Few military aircraft have revolutionized attack aviation quite like the LTV A-7 Corsair II. Initially designed in the 1960s, this remarkable aircraft introduced engineering innovations that were decades ahead of its time, including the first modern heads-up display and digital navigation system in a U.S. military aircraft. The A-7 Corsair II emerged as a testament to practical engineering excellence. Though subsonic, the aircraft proved that sophisticated avionics and precision engineering could outweigh raw speed. The A-7E variant, in particular, demonstrated how thoughtful design choices and advanced systems integration could create an exceptionally effective attack aircraft. Subsequently, many of its pioneering features became standard in modern military aviation, from its digital computer implementation to its innovative weapons delivery systems. This video will explore the groundbreaking engineering decisions that made the A-7 Corsair II a milestone in aviation history, examine its revolutionary design philosophy, advanced and lasting impact on aircraft development. Revolutionary design philosophy. The development of the LTV A-7 Corsair II marked a significant shift in military aircraft design philosophy. During the early 1960s, the U.S. Navy made a bold decision to prioritize practical effectiveness over raw speed, leading to a remarkable series of engineering choices. The engineering team made a calculated decision to restrict the A-7 Corsair II to subsonic speeds. This choice, while unconventional for its era, proved strategically sound. By foregoing supersonic capabilities, engineers created an airframe that was notably smaller and more efficient. Furthermore, this decision allowed for a more straightforward manufacturing process, resulting in an aircraft that could be produced in larger quantities compared to supersonic alternatives. The development of the A-7 Corsair II stands as a remarkable example of a cost-effective engineering approach, reflecting a commitment to innovation and practicality in military aircraft design. This achievement was realized through several strategic decisions aimed at reducing costs while maintaining performance and operational effectiveness. One of the key aspects of this approach was the simplification of the airframe, which was derived from the proven design of the F-8 Crusader. By leveraging an existing platform, designers minimized the need for extensive research and development, streamlining the overall process. The fuselage was shortened and featured a rounded nose, a design modification that not only distinguished the A-7, but also contributed to structural efficiency and manufacturing ease. To meet the demands of carrier-based operations, the aircraft was equipped with strengthened landing gear, ensuring durability and reliability during the rigors of naval aviation. Additionally, the installation of a non-augmented turbofan engine represented a deliberate choice to prioritize fuel efficiency and simplicity over more complex propulsion systems, further aligning with the overarching goal of cost reduction. The results of these design choices were extraordinary. The A-7's development timeline was one of the fastest for a combat aircraft since the end of World War II, demonstrating the effectiveness of a focused and pragmatic approach. This remarkable feat underscores the success of its designers in balancing innovation, cost management, and operational readiness. The engineering team expertly integrated proven technologies while introducing strategic modifications. Specifically, they retained the F-8's powered flight controls, but implemented conventional outboard ailerons instead of the F-8's drooping ailerons. The A-7 Corsair II's wing design was meticulously optimized to balance performance, functionality, and adaptability. Large slotted flaps were incorporated to improve low-speed control, a critical feature for carrier-based operations. The placement of the wing fold was strategically chosen to enhance compatibility with carrier storage and handling requirements. The broader wing structure was also designed to support increased payload capacity, allowing the aircraft to carry a more substantial arsenal or additional equipment. The design philosophy emphasized practical functionality over theoretical performance. Consequently, the A-7 featured a larger cross-section than its predecessor, accommodating more fuel capacity and advanced avionics systems. This approach resulted in an aircraft that could carry nearly double the payload of its predecessor, the A-4 Skyhawk. The engineering team's focus on practical innovation extended to the aircraft systems integration. Notably, they incorporated advanced avionics that enabled precise weapons delivery from greater standoff distances, significantly improving survivability compared to contemporary aircraft. Advanced avionics integration. The A-7 Corsair II stands out in aviation history for its groundbreaking avionics suite that set new standards for combat aircraft. The integration of advanced systems marked a decisive shift in military aviation technology. The A-7 Corsair II marked a significant milestone in aviation technology by pioneering the integration of the first fully instrumented head-up display, called HUD for short, in an American combat aircraft. This advanced system, designated the AVQ-7V HUD, was developed and manufactured through the collaboration of Elliott Flight Automation and Marconi. It revolutionized the way pilots interacted with flight data, providing critical information directly in their line of sight, which significantly enhanced situational awareness and operational effectiveness. The HUD was designed to display a range of essential flight parameters including dive angle, airspeed, altitude, drift, and an aiming reticule, enabling pilots to make precise and informed decisions during high-pressure combat situations. Beyond these fundamental capabilities, the system introduced groundbreaking features that redefined weapon delivery and targeting accuracy. One of these features was the continuously computed impact point, which provided real-time calculations for weapon release, ensuring precise targeting even in dynamic environments. The system also included a bomb fall line feature, which visually represented the predicted impact points of bombs, aiding pilots in accurate manual delivery. Additionally, the HUD offered the continuously computed release point, a sophisticated function that enabled automatic weapon delivery by calculating the optimal release point based on flight parameters and target location. These innovations not only enhanced the combat effectiveness of the A-7, but also set new standards for avionics technology in military aviation. The AVQ-7V HUD became a benchmark for future HUD designs, illustrating the transformative impact of integrating advanced instrumentation into fighter aircraft. This groundbreaking development underscored the A-7's role as a technological trailblazer and a cornerstone of modern combat aviation systems. The navigation systems of the A-7 Corsair II introduced groundbreaking advancements in aviation technology, significantly enhancing the aircraft's operational precision and reliability. At the core of these capabilities was the AVQ-116 radar system, which was later upgraded to the more advanced AVQ-126 model. This radar seamlessly integrated with the aircraft's digital navigation suite, creating a sophisticated network of systems that allowed for precise and efficient navigation in diverse operational scenarios. One of the most innovative components of the navigation suite was the Projected Map Display System, or PEMS, a remarkable tool that transformed the way pilots visualized their surroundings and planned their routes. The PEMS featured dual-scale mapping functionality, which enabled pilots to view their position on two map scales, offering both a broad overview and detailed localized data for enhanced situational awareness. This system also incorporated an inertial navigation system integration, providing high-resolution overlays of the aircraft's position on tactical pilotage charts and jet navigation charts. This integration ensured that pilots could navigate with exceptional accuracy, even in challenging environments or during complex missions. Further enhancing its capabilities, the navigation system included a waypoint navigation feature that allowed for hands-off flight to as many as 9 programmable points. This capability not only reduced pilot workload, but also improved mission efficiency by automating key aspects of route planning and execution. Together, these features represented a substantial leap forward in navigation technology, setting the A-7 apart as a highly advanced platform for its time. The integration of cutting-edge radar, digital systems, and map displays underscored the aircraft's role as a pioneer in modern avionics and a testament to the transformative potential of innovative engineering. The integration of an IBM navigation and weapons delivery computer established new benchmarks for accuracy and efficiency. The system achieved remarkable precision with a circular error probable of 60 feet. Notably, when properly calibrated by Vought technical representatives, experienced fleet aviators could achieve CEPs of less than 5 meters. The digital systems of the A-7 Corsair II provided a range of significant operational advantages that set it apart from its contemporaries. One notable benefit was the remarkably rapid ground alignment process, which required only 2.5 minutes, substantially faster than the 13-minute alignment of the F4 Phantom II. This efficiency allowed the A-7 to be mission-ready in a fraction of the time, enhancing its overall responsiveness and utility in dynamic combat scenarios. Additionally, the aircraft was equipped with automated carrier landing capabilities, made possible through seamless integration with a data link system. This feature significantly improved landing precision and safety, particularly during challenging conditions at sea. The A-7 also excelled in all-weather attack capabilities, thanks to its advanced avionics and digital systems, enabling effective operations in a wide range of environmental conditions. The A-7E variant particularly excelled in weapons delivery accuracy through its state-of-the-art navigation and bombing computers. The system's sophistication allowed for accurate weapons delivery from greater standoff distances, essentially improving aircraft survivability compared to contemporary fighters. Powerplant engineering innovations. The powerplant engineering of the A-7 Corsair II exemplified a careful balance between performance and efficiency. The aircraft's engine selection and optimization played a crucial role in its operational success. The initial A-7 variants utilized the Pratt & Whitney T30 P6 turbofan engine, producing 11,345 lb of thrust. This non-afterburning turbofan marked a departure from conventional fighter jet engines of the era. Nonetheless, early operations revealed certain limitations, primarily compressor stalls and insufficient thrust. Engineers introduced a series of progressive enhancements to the A-7's propulsion system by developing several engine variants, each tailored to meet the evolving performance demands of different aircraft models. The earlier 7 variants were powered by the T30 P6 engine, which delivered a thrust output of 11,345 pounds-force, providing a reliable foundation for the aircraft's initial operational capabilities. As the A-7 evolved, the A-7D variant was equipped with the more powerful F41 A1 engine, capable of producing 14,500 lb of thrust. This upgrade significantly enhanced the aircraft's performance, offering greater payload capacity and improved overall efficiency. Similarly, the A-7E variant featured the T41 A2 engine, which delivered 14,250 lb of thrust, striking a balance between power and operational refinement. These incremental advancements in engine technology not only increased the A-7's performance across its variants, but also underscored the commitment to continuous improvement and adaptability in its design. The transition to the Allison F41 A1 turbofan, a licensed version of the British Rolls-Royce Spey, proved transformative. This powerplant delivered 14,500 lb of thrust, offering a substantial performance boost. The engine selection was pivotal in achieving the desired balance between performance and efficiency. The A-7's turbofan engine configuration exemplified remarkable fuel efficiency achieved through a series of innovative design features. By moving larger masses of air at lower velocities, the engine maximized aerodynamic efficiency while reducing energy waste. This design philosophy translated into exceptional performance metrics, particularly during sustained flight and operational scenarios. For instance, an A-7D equipped with 12 500-pound bombs cruising at 480 miles per hour at an altitude of 350 pounds of fuel per hour. This level of efficiency was unmatched among its peers and highlighted the aircraft's suitability for extended missions. Similarly, during aircraft carrier recovery operations, the A-7 demonstrated a fuel consumption rate of approximately 30 pounds per minute, a significant improvement compared to the 100 pounds per minute required by the F4 Phantom. The turbofan configuration delivered unprecedented fuel efficiency, with specific fuel consumption approximately 1/6 that of an F100 Super Sabre at equivalent thrust. Hence, the A-7 achieved exceptional range without sacrificing payload capacity. Albeit the initial maintenance requirements were promising at 11.5 man-hours per mission, exposure to harsh marine conditions often doubled these figures after several years of service. Therefore, engineers implemented continuous improvements to enhance reliability and maintainability throughout the aircraft's service life. Weapons system integration. Weapons integration on the LTV A-7 Corsair II exemplified precision engineering combined with versatile combat capabilities. The aircraft earned the nickname Navy's bomb truck through its remarkable weapons carrying capacity and delivery accuracy. The A-7 Corsair II showcased remarkable versatility with its ability to perform a wide range of mission types. The aircraft was highly effective in ground attack and precision bombing, as well as in electronic warfare and jamming operations. Additionally, it proved its capability in waterway mining, search and reconnaissance missions, and even in in-flight refueling operations. This broad operational range highlighted the A-7's adaptability and effectiveness in diverse combat scenarios. Notably, the A-7D achieved the lowest combat loss rate among U.S. fighters, with only 6 losses in 12,928 combat sorties. Similarly, the aircraft proved second only to the B-52 Stratofortress in ordnance delivery on strategic targets in Hanoi. The integration of advanced targeting systems established new benchmarks for weapons delivery accuracy. The A-7E was equipped with advanced targeting technologies that significantly enhanced its operational capabilities. The Target Recognition Attack Multi-Sensor System improved target identification, allowing for greater accuracy. Additionally, the forward-looking infrared system enabled precision night attack capabilities, while the precision avionics vectoring equipment facilitated laser spot designation, further refining the aircraft's targeting precision. The aircraft's digital navigation system, coupled with the IBM weapons delivery computer, enabled precise bomb delivery from extended standoff distances. Essentially, this innovation enhanced survivability without compromising accuracy. The A-7E demonstrated remarkable precision, achieving 4 to 6 mils accuracy during armament service acceptance trials. The A-7 Corsair I's weapons carrying capacity marked a substantial advancement over its predecessors. The aircraft could transport up to 15,000 pounds of ordnance distributed across 6 underwing pylons. This represented nearly double the payload capacity of its predecessor, the A-4 Skyhawk. The A-7 was equipped with a primary armament of one M61, a 120mm rapid-fire cannon, integrated into a sophisticated weapons system. This system featured the continuously computed impact point for real-time targeting, allowing for precise weapon release calculations. It also included a bomb fall line that displayed predicted impact points, aiding in accurate strike execution. Additionally, the system offered multiple weapon delivery modes, each optimized for different mission profiles, enhancing the aircraft's flexibility and effectiveness in various combat scenarios. The aircraft's combat performance validated these innovations. Throughout Operation Desert Storm, the A-7 executed 37 combat missions over Iraq and Kuwait. Likewise, its precision bombing capability in adverse weather conditions established it as a primary asset for both the U.S. Navy and the Air Force. Structural engineering achievements. Structural resilience formed the backbone of the LTV A-7 Corsair II's engineering excellence. The aircraft's robust design incorporated multiple protective features that established new standards in military aviation durability. The A-7 Corsair II's structural integrity centered on a comprehensive protection system. Remarkably, the engineers implemented a triple redundant hydraulic system to ensure control surface functionality even under combat damage. The aircraft's vital systems received additional protection through strategic armor placement around the cockpit and critical components. Essential durability features included duplicate hydraulic systems for enhanced survivability, armor plating surrounding mission-critical components, reinforced structural components for extended service life, and advanced semi-damping system for nose gear stability. The A-7 Corsair II's landing gear system was meticulously engineered to meet the rigorous demands of carrier-based operations, ensuring reliable performance during takeoff landing, and maneuvering on the deck. The aircraft's tricycle landing gear configuration was thoughtfully designed with a series of innovative features tailored to the unique challenges of naval aviation. The nose gear, equipped with a twin-wheel, steerable system, was specifically designed to be compatible with carrier catapults. This system allowed for greater maneuverability on the deck, with the steering capability extending up to 60 degrees. This provided exceptional precision when positioning the aircraft for launch or recovery, a critical factor for ensuring smooth and safe operations in the confined space of an aircraft carrier's flight deck. For the main landing gear, the A-7 incorporated single-wheel units with a forward retraction mechanism into the fuselage. This design maximized the use of available space, ensuring that the landing gear would not interfere with the aircraft's overall aerodynamic profile, while providing the structural strength needed to withstand the stresses of carrier landings. Additionally, the aircraft featured a Stinger-type arresting hook located under the tail section, designed to engage the carrier's arresting wires during landing. This component played a crucial role in ensuring a safe and controlled landing, allowing the A-7 to safely stop after landing on a moving aircraft carrier. Together, these features demonstrated a high level of engineering foresight, optimizing the A-7's ability to operate efficiently and safely in the challenging environment of aircraft carrier operations. The evolution of the A-7 Corsair II's material composition demonstrated forward-thinking engineering approaches. Originally equipped with steel and aluminum armor plating, the aircraft underwent substantial improvements with the introduction of boron carbide armor in later variants. This material advancement offered superior protection while reducing overall weight. The thoughtful material selection contributed to the aircraft's impressive maintenance statistics. Early production models required merely 11.5 maintenance hours per flight hour. However, extended exposure to corrosive marine environments often doubled these maintenance requirements. The structural engineering achievements of the A-7 Corsair II proved their worth in combat scenarios. Throughout its service in Vietnam, the aircraft maintained one of the lowest loss rates, with only 6 aircraft lost in nearly 13,000 combat sorties. Essentially, these durability features enabled the A-7 to operate effectively across diverse combat environments, from carrier operations to land-based missions. Flight control systems. Advanced flight control engineering distinguished the LTV A-7 Corsair II from its contemporaries. The aircraft's sophisticated control systems represented a remarkable blend of reliability and innovation. The A-7 Corsair II featured a pioneering triple redundant hydraulic system for its flight controls, establishing new standards in combat survivability. This redundancy proved essential in ensuring aircraft control even after sustaining battle damage. The system's effectiveness became apparent through the primary control system for essential flight controls, the secondary system for auxiliary functions, and the emergency backup system for critical operations. The A-7 Corsair II's engineering team developed an advanced control surface configuration that significantly enhanced the aircraft's handling and overall flight characteristics. The wing design was at the heart of these improvements, featuring full-span leading-edge flaps that optimized takeoff performance, ensuring smooth and efficient liftoff even in demanding conditions. Additionally, large slotted flaps were positioned on the inner trailing edge of the wing to further improve the aircraft's ability to maintain stability and control during landing approaches, providing increased lift at slower speeds. The aircraft's control surfaces included conventional outboard ailerons designed for precise roll control, which allowed the pilot to maintain fine control over the aircraft's roll axis during both high-speed flight and complex maneuvering. The large slotted flaps were another essential feature, designed to improve landing performance by enhancing lift at lower speeds, allowing the A-7 to perform safer and more efficient landings, especially during carrier operations. Spoilers were strategically positioned forward of each flap to assist with lift reduction, further aiding in the aircraft's handling characteristics by allowing for more controlled descent and improved stability during the approach. To complement these surfaces, the A-7 was equipped with a belly-mounted air brake, which provided additional speed control, helping the aircraft to slow down quickly when needed, particularly during landing or evasive maneuvers. An innovative automatic maneuvering flap system was also incorporated into the design, which functioned when the aircraft was flying below Mach 0.7. This system extended the flaps partially at a 14.75- angle of attack and retracted below 10.5 units, enhancing turn performance and maneuverability at lower speeds. This feature marked a significant improvement in the A-7's agility and handling, allowing it to execute sharp turns and other high-performance maneuvers with greater ease, making it a highly responsive platform in both combat and operational environments. The control augmentation system proved fundamental to the A-7's flight characteristics. Without this system, the airframe demonstrated considerable difficulty in maintaining stable flight. The A-7 Corsair II incorporated a range of stability augmentation features designed to enhance its flight performance and ease of control. At the heart of these features was the Automatic Flight Control System, or AFS, which provided several critical functions. These included heading control mode, which ensured the aircraft maintained its course, altitude maintenance to keep the aircraft at a consistent height, and attitude stabilization to prevent unwanted pitch and roll movements. Additionally, the system was capable of regulating airspeed, ensuring optimal flight conditions throughout the mission. Complementing the AFS was an advanced control integration system, which included several mechanisms for further enhancing stability. The yaw stabilization system played a vital role in maintaining the aircraft's directional stability, while turn coordination assistance ensured smooth and coordinated turns. Furthermore, the slip correction mechanisms helped prevent any unintended side-to-side movement, contributing to the aircraft's overall smooth and precise handling. The nose gear steering system exemplified the sophisticated integration of flight controls, offering up to 60 degrees of movement through hydraulic actuation. Primarily, this system provided automatic shimmy damping when de-energized, ensuring smooth ground operations. The engineering team incorporated multiple safety features into the control systems. For instance, the automatic recentering of the nose gear occurred upon retraction, or when the right gear weight on wheel sensor detected no ground contact. Essentially, these innovations established new benchmarks in military aircraft control system design. Maintenance engineering. Maintenance engineering excellence distinguished the LTV A-7 Corsair II through its innovative approach to serviceability and reliability. The aircraft's design prioritized ease of maintenance alongside combat effectiveness, establishing new standards in military aviation maintenance. The engineering team implemented groundbreaking accessibility features throughout the A-7 Corsair II's design. First of all, the aircraft featured access panels covering 50% of its skin area, positioned at heights that eliminated the need for maintenance ladders or service stands. This carefully considered design led to several important benefits, including the ability to conduct quick inspections, allowing for faster checks and assessments. The system also provided streamlined access to components, making it easier for maintenance crews to reach critical parts of the aircraft. As a result, the need for extensive maintenance equipment was reduced, leading to a more efficient servicing process overall. These design choices significantly enhanced the speed and effectiveness of maintenance operations, ensuring the aircraft remained operational with minimal downtime. The A-7's modular architecture established new benchmarks in maintenance efficiency. This approach proved successful as newly manufactured E models required merely 11.5 maintenance hours per mission. The modular design of the A-7 Corsair II included several key features that greatly enhanced its maintenance efficiency. The engine bay was equipped with quick access panels, allowing for easy servicing of the powerplant and minimizing downtime. The Avionics bay featured a modular rack system, which facilitated the installation and replacement of electronic components with ease. The weapon systems were designed with plug-and-play capability, enabling straightforward upgrades to keep pace with evolving technologies. Additionally, the control surfaces incorporated easily replaceable hydraulic components, ensuring that maintenance tasks could be completed quickly and effectively, reducing overall operational disruptions. Primarily, this modular approach facilitated the rapid integration of new capabilities. The A-7E demonstrated this flexibility through numerous upgrades, notably the incorporation of the low-altitude night attack pod system in 1986, which was successfully implemented across 231 aircraft. Throughout its service life, the A-7 Corsair II saw ongoing improvements to its reliability. The engineering team concentrated on enhancing several key areas to ensure the aircraft's performance and longevity. In terms of digital systems, advancements included the implementation of ring laser gyro technology, the integration of a more advanced tactical mission computer, and the refinement of inertial measurement systems for greater precision. Structural durability also saw significant upgrades, with enhanced corrosion protection applied to critical components, ensuring the aircraft could withstand the harsh conditions of extended service. Additionally, the landing gear components were strengthened to improve their resilience, and the hydraulic systems were upgraded to provide more reliable performance under demanding conditions. Undoubtedly, these improvements contributed to the aircraft's exceptional combat readiness. The A-7's maintenance program demonstrated remarkable efficiency, although exposure to harsh marine conditions often doubled the initial maintenance hour requirements after several years of carrier operations. The aircraft's reliability improvements extended to its avionics systems. The ANAC 126 radar received substantial subsystem upgrades to enhance reliability. Essential to these improvements was the implementation of the automated maneuvering flap scheme, which optimized performance while reducing maintenance requirements. The engineering team's commitment to reliability manifested in the development of the A&D-K replacement inertialment system during the late 1980s. This upgrade made the A-7 one of the first aircraft to employ ring laser gyro technology. The integration of these advanced systems required careful consideration of maintenance procedures, ensuring that technological sophistication did not compromise serviceability. The maintenance engineering achievements of the A-7 Corsair II played a crucial role in its operational success. The aircraft's design allowed for rapid deployment and sustained combat operations, as demonstrated by its extensive service record. The Oklahoma City Air Logistics Center assumed logistics program responsibility for a 7D aircraft by July 1, 1975, overseeing numerous upgrade programs that enhanced the aircraft's capabilities while maintaining its fundamental maintenance advantages. Engineering impact and legacy. The LTV A-7 Corsair II's engineering achievements established enduring benchmarks in military aviation design and technology. First and foremost, its combat record validated its engineering excellence, with only 6 aircraft lost in nearly 13,000 combat sorties during the Vietnam War. The A-7's pioneering integration of digital systems and advanced avionics influenced numerous subsequent aircraft designs. In essence, its implementation of the head-up display and digital navigation systems became standard features in modern military aircraft. The aircraft's impact was far-reaching, encompassing advancements in precision targeting systems, the development of digital weapons delivery computers, the integration of sophisticated navigation solutions, and the introduction of advanced cockpit displays. These innovations collectively elevated the standards of modern combat aviation, enhancing operational accuracy, efficiency, and pilot situational awareness. The F-117 stealth fighter program notably selected A-7 pilots for testing, as the aircraft's cockpit workload and single-seat configuration closely matched the requirements of next-generation aircraft. The service life of the A-7 Corsair II provided invaluable insights into key engineering principles that shaped modern aviation. One of its most significant achievements was the pioneering integration of comprehensive digital systems, making it the first operational combat aircraft to do so. This innovation set a new standard for avionics and system automation. The A-7 also excelled in maintenance efficiency, requiring only 17 maintenance hours per flight hour, a benchmark that reflected a thoughtful design for operational sustainability. Its combat performance was equally noteworthy, achieving the highest bombing accuracy among its contemporaries and underscoring its precision and reliability in mission-critical scenarios. Additionally, the A-7 demonstrated exceptional operational flexibility, successfully adapting to a wide range of combat environments and mission profiles. The aircraft's success in Operation Desert Storm, where it executed 37 combat missions over Iraq and Kuwait, proved the enduring relevance of its engineering approach. As a result, many of its design principles influenced the development of subsequent attack aircraft. The A-7's contributions to aviation industry standards were substantial and long-lasting. The aircraft's advanced avionics suite, primarily its an AC-126 radar system integrated with the digital navigation computer, established new benchmarks for precision attack capabilities. The success of the A-7 program in achieving its development timelines and cost targets provided critical insights for future aircraft development. A key factor in its cost-effective approach was the decision to base the design on an existing airframe, which enabled rapid prototype development and streamlined production processes. This strategy not only reduced costs but also accelerated the aircraft's entry into service. Equally important was the program's focus on system integration, which saw the implementation of a comprehensive digital architecture. This included advanced weapons delivery systems and sophisticated navigation solutions, setting a new standard for functionality and efficiency in combat aircraft. The A-7E variant, in particular, showcased the effectiveness of incremental improvements, incorporating target recognition attack multi-sensors and forward-looking infrared systems. These innovations became standard features in subsequent attack aircraft. The aircraft's operational history spans multiple conflicts from Vietnam to Operation Desert Storm, demonstrating remarkable adaptability. Its final combat missions in 1991, flown by VA-46 and VA-72 squadrons from USS John F. Kennedy, marked the culmination of a design philosophy that prioritized practical effectiveness over theoretical performance. The A-7's influence extended beyond its active service life, with its digital systems architecture influencing the development of fourth-generation fighter aircraft. The success of its integrated avionics suite, which enabled precise weapons delivery from greater standoff distances, established new standards for combat aircraft effectiveness. The Portuguese Air Force continued operating the aircraft until 1999, followed by the Hellenic Air Force until 2014, affirming the durability and relevance of its engineering design. The aircraft's legacy encompasses not only its combat achievements, but also its role in advancing military aviation technology and establishing enduring design principles that continue to influence modern aircraft development. The A-7 Corsair II exemplifies practical engineering excellence, proving that thoughtful design choices can often outperform raw performance metrics. Through its groundbreaking digital systems and advanced avionics, the A-7 set new standards for military aviation technology. Its achievements in digital navigation, HUD integration, and weapons delivery accuracy were unmatched by contemporary aircraft. How do you think the A-7's innovations influenced modern aircraft? What are some features from older aircraft that you think should still be applied today? We would love it if you like the video and comment before you start another video. Thank you for watching.